Hi there, this is a brand new section. Here we are going to talk about recursion. Firstly, let's identify what recursion is. By definition, it's a way of solving a problem by having a function call itself. In computer science, it's a method of solving a problem where the solution depends on the solution to the smaller instance of same problem. Such problems can generally be solved by iteration as well. The real-life example for recursion can be a Russian nesting doll. Hopefully, you have seen a set of Russian doll. If not, this is the picture how it looks like. At first, you just see one figure, usually painted wood, that looks like this. If you remove the top half of this doll, you see another slightly smaller Russian doll inside it. You can remove this doll from here and again separate its top and bottom halves. Here again you will see another smaller doll. And if you do it once more, you will see another smaller one. And we can keep going until we find the smallest Russian doll. It is just one piece, so it does not open. As you see, a Russian doll is a sequence of similar dolls inside each other that can be opened, but every time the size gets smaller and smaller. Each time you open a doll, a smaller version of doll will be inside, and you repeat the process until you reach the final doll that cannot be opened. Here, if you think of this big doll as a problem, you can see that the problem gets the smaller instance of the same problem until we solve it. So this technique, making the problem smaller and smaller, is called recursion. There are many properties of recursion. So let's see properties of recursion based on this real-life example. So here, our example of Russian dolls conform with the main properties of recursion. So the first property is performing the same operation multiple times with different input. So we perform this process of opening Russian dolls multiple times, and every time we open it with different size of dolls, which means that the input is different. So first we start from the bigger one, then we continue to the which is smaller, then again we open the smaller one, and this continues like this. So here we opened 10 different sizes of Russian dolls. As you notice that the process of opening all these dolls is always same. That's why in the property of recursion it says the same operation is being performed. So our operation here was opening Russian dolls. Now the second property of recursion is in every step we try smaller inputs to make the problem smaller. Similarly, in the case of opening Russian dolls, we try to make the problem smaller. First we open the big doll again, and then the next smaller, and then the next smaller, and so on. Now you might be interested why we are making the problem smaller. Because every time we make the problem smaller, this makes it easier to find the solution at the end, which is the smallest Russian doll at the end that does not contain any other one. This is the solution for this problem. Finally, the last property of recursion is that base condition is needed to stop recursion. Otherwise, infinite loop will occur. Basically, the base condition is the condition after that we will not do any more recursion. We will stop the recursion because we either would have found the answer or the answer does not exist. In the case of Russian dolls, we open the first one, then the second one, then the third one, until we reach the one which is the smallest one. So we have to mention that when we reach the smallest one that cannot be opened, we need to stop here. Now you might be interested, what if we don't provide a base condition? In this case, the system will not know when to stop recursion, and this will lead to infinite loop. So no one wants to get inside an infinite loop, because you will never come out of it. There are even a lot of programming jokes about infinite loop. The one that I like most is a programmer's wife tells him as he leaves the house, while you are out, buy some milk. He never returns home and the universe runs out of milk. You see that she hasn't provided base condition here, that's why her husband is gone for forever. So hopefully you understand all properties of recursion. So let's convert this Russian doll example into the code so we can express it in the computer science. So our code for this Russian doll example will be like this. Here we provide base condition as when the doll equals 1. So all dolls are open. So here I took as a 1 the smallest one, which cannot be opened. Otherwise, every time we are calling this same function with one smaller and opening each doll. So let's recap what we have learned here. So here we have learned that by definition, recursion is a way of solving problem by having a function to call itself, and we provided a real example of Russian dolls, which makes the understanding the logic of recursion easy. So that's all for this lecture. Hopefully you understand the logic behind the recursion. In case you still have problems understanding the recursion, you don't need to worry about this because we will talk about it in a lot more details in the next videos. So see you there. Alright, in this video we will look at why we need recursion. This is a quite difficult topic and many people cannot get the concept straight away. But if you keep practicing, then the concept becomes clear. So you might be interested why we need recursion. There are many reasons for this. First of all, recursive thinking is really important in programming, and it helps you break down big problems into smaller ones. Often, recursive solution can be simpler to read than the iterative one. Recursion is used all the time, in nearly every field, in nearly every language. If we compare recursive way of writing code with the iterative way, we can easily see that the recursive code is easy to write. Iterative way of code is basically where we use loops. So you might be interested, if it is easier to write code, can we choose recursion over iteration? The answer is no, because there are situations where iteration performs faster than recursion. So it depends on the situation. So when do we choose recursion? A good hint here is that if you can divide the problem into similar subproblems, then you can use recursion. The important point here is the subproblem must be similar, otherwise recursion is not a choice. So how can we know that the subproblem is similar in the nature? So when you hear a problem beginning with the following statements, it's often, but not always, a good candidate for recursion. Design an algorithm to compute AND, write a code to list the AND, implement a code to compute all. Finally, the best way to identify a recursive problem is practice. The more problems you do, the easier it will be recognized recursive problems. The second reason to use recursion is the prominent usage of recursion in data structures like trees and graphs. So when we are dealing with trees, the recursion becomes almost mandatory to use. So in the upcoming sections, we will explain tree data structures, and there you will see that without recursion, some operation on trees become almost impossible. But it doesn't mean that you cannot use iteration over there, but in this case, recursion is preferable due to the easier nature to write code. So without learning recursion, the upcoming sections will be extremely difficult to understand. So the third reason is that many big companies ask questions related to recursion during the interview. So to pass these interviews, to get better job, recursion becomes extremely important. Here, at the end of this section, I will explain top questions related to recursion that are asked in the interviews of companies like Apple, Google, Facebook, and Microsoft. So the fourth reason is that recursion is used in many algorithms. As you remember, when we discussed the types of algorithms in one of our previous lectures, we talked about divide and conquer, greedy, and dynamic programming. So the recursion is prominently used in these types of algorithms. So without knowledge of recursions, these topics become very difficult to learn. So now you have an idea of why we need recursion, and hopefully you understand why it's important to us. So see you in the next lecture. Alright guys, welcome back. So in the last video, we have learned why we need recursion, and we specified various reasons for the need for recursion. So in this module, we are going to look at declaration format of recursion method and how it works. So when we create a recursive method, we need to take into account two conditions. A condition where a method calls itself with a smaller values, and the second condition to exit from an infinite loop. So taking into account these two conditions, the basic syntax of recursion will be like this. From the syntax, we can easily see that the mentioned two conditions are implemented over here. So first it checks given condition. If it is satisfied, then it returns some value over here. Otherwise, it continues to call recursive method recursively until the condition is met. Before explaining how recursion works internally, let's look at how a normal method works internally. Okay, let's imagine we have 4 different functions, and each of these functions calls one another. So the first method calls the second method, then prints out that I am the first method. And the second method calls the third one, and then prints out I am the second method. And the third method conveniently calls the fourth method. Then again, it prints out that I am the third method. And finally, fourth method prints out I am the fourth method without calling any method. So let's see what's happening on the stack memory when we call first method. The stack memory is maintained by the system for the method invocation. You may already know that stack memory works on leave method, which means that the last entered will be removed first. Here, push method is used to insert into a stack, and the pop method is used for removal. If you don't know what the stack is, we will discuss it in the stack section in detail, so you don't need to worry about it. Okay, here we start from first method. As soon as we call first method, the first statement that we see within the first method is to call second method. So the control goes to the second method. After completing the second method, it needs to come back to first method to execute the print statement after the second method calling. So the system needs to store the first method somewhere to come back for executing the rest of code, which is within the first method once the second method execution is done. So the system will push the first method to the stack memory. So in this way, the system remembers that it needs to come back to the first method. Okay, if you look at the second method, we see that this method also calls another method, which is third method. So the system once again needs to store the second method to come back to execute print statement after third method. This one over here. So the second method will be pushed to stack as well. And this is applicable for third method because it also calls another method within before executing the rest of the code. So it will be pushed to stack as well. The last method is here fourth method, which is executing one line of code without calling any function, which means that the system does not need to store it somewhere for calling back. So it will not be inserted in stack memory. So after finishing execution of fourth method, how does the system know that it needs to go to back and execute third method, not the second method? So this will come from stack memory. As we said, it works based on last in, first out strategy. So the last method that is added to stack is the third method. So this method will be called by the system as a next step to execute the rest of code, which is printing I am the third method. So after this statement, we know that third method is done. So it will be popped out from the stack memory. And here again, the next step will be from stack memory as well, which is second method. So the second method will be called and the print statement inside second method will be executed. And with this, we know that the execution of second method is complete, which means that it will be popped out from the stack memory. Now the system one more time refers to the stack memory and calls first method and execute the print statement inside the first method, and with this, the execution of first method is complete. So the first method will be popped out from the stack memory. So with this, all execution is complete. So now it should be clear how method execution is managed in stack memory. Okay, let's see how a recursive method is stored in stack memory. As an example, we will look at this method over here. This is a recursive function that calls itself. First, it checks if the entered parameter n is less than 1, it prints out that n is less than 1, else it calls itself with parameter n minus 1. So to make things clear, let's run this function for parameter of 4. And let's see how this will be managed in stack memory. When we run this function with parameter of 4, first the system checks that whether 4 is less than 1. We see that 4 is greater than 1. So this means that else statement will be executed, which is calling the recursive function with parameter 3. So recursive method with parameter 4 will be stored in stack memory to come back for executing the print statement after this over here. So when running the function with parameter 3, the system once again checks that if whether the 3 is less than 1, we see that 3 is greater than 1. So this means that else statement will be executed, which is calling the recursive method with parameter 2. So the recursive method with parameter 3 will be stored in stack to come back for executing the print statement after this. So once again, when running the recursive function with the parameter 2, the system checks first if condition. We see that 2 is greater than 1, which means that else statement will be executed, which is calling recursive method with parameter 1. So the recursive method with parameter 2 will be stored in stack memory. So once again, when we're running the function with parameter 1, the system checks that this condition, and we see that 1 equals to 1, so which means that else condition will be executed, which is calling recursive method with parameter 0. So the recursive method with parameter 1 will be stored in stack memory. So when we call recursive method with parameter 0, we see that 0 is less than 1, so the print statement executed, and no need for storing method in stack memory. So to continue the execution, system refers to the stack memory again, so the last method is pushed to stack will be the first executed, which is recursive method with parameter 1 in our case. So it will call the method with parameter of 1, which will print n out. So in our case, print is 1 because after calling the recursive method with parameter 0, which is 1 minus 1, then we print n here. In our case, n is 1. So the output from recursive method with parameter 1 will be 1. And after calling this method from the stack, it will be popped out from the stack memory. So once this statement executed, the recursive method with parameter 1 is completed. So the system will go to the next method, which is located in stack memory. In our case, it's a recursive method with parameter 2, and this will again print 2. Because when you call this method with parameter 2, it's calling recursive method with parameter 1, it prints out 2, because n is 2. Then after calling this function, the method from stack memory will be popped out. So as a next step, the system will call the next method from stack memory, which is the recursive method with parameter 3, and this will print out 3 as an output. So after executing this method, the recursive method with parameter 3 will be popped out of the stack memory. And as a next step, the last method from the stack will be called, which is recursive method with parameter 4. So when you call this function with parameter 4, after calling this recursive method with parameter 3, here we have output 3, it will print out n, which is 4 in our case. And then recursive method with parameter 4 will be popped out of stack memory. So this is how a recursive method is managed in stack memory internally. Hopefully everything is clear now. So let's recap what we have learned from this lecture. We understood that stack memory is used by the system for managing recursive calls. So every time recursive method calls itself, the system stores it in the stack for coming back. Because there are execution statements left after calling itself, this means that system somehow should remember the point where it stops to call recursive method with different parameter based on the condition for coming back. This is done by storing methods in stack memory. And the stack memory manages the value based on leave method, which is last in, first out. And this is all for this lecture. Hopefully you have understood everything clearly. So see you in the next lecture. Hi there. Now in the last video, we have learned how recursion works internally. And we saw what's happening in the stack memory when we call a recursive method. And as you remember, in the introductory lecture of this section, we said that any problem that can be solved using recursion can be solved using iteration. Here, in this video, we will compare recursion versus iteration. As we said, all recursive algorithms can be implemented iteratively, although sometimes it's much more complex to do it. Let's look at the example which was implemented in both ways. Here, both methods calculate nth power of 2. As a parameter, both methods, as you can see, take n, which is an integer number. In the recursive function over here, we have an if condition, here, which is a base condition to stop infinite loop. And then, if the condition is not satisfied, the function calls itself recursively and return a power of 2. In the iterative solution, we start by creating two variables, which is I and power. So, while I less than n, it multiplies power with 2, and in each iteration, I is increased by 1. So if you look at this piece of code carefully, we can see that recursion code is easy to write compared to iterative one. You might not notice it here in this code because it's a very simple function. But there are many situations that converting a recursive function to an iterative function is extremely difficult. The second point here is a conditional statement decides the termination of recursion, while a control variable's value decides the termination of iteration statements. In this case, value of I decides the termination. Here in recursive function, infinite recursion can lead to system crash, whereas in iterative function, infinite iteration consumes CPU cycles. The next point is recursion repeatedly invokes the mechanism, consequently overhead of method calls. This can be expensive in both processor time and memory space, while iteration does not. Recursive algorithms can be very space inefficient. As we explained in previous video, each recursive call adds a new layer to the stack, which means that if your algorithm resources to the depth of n, it uses at least O(n) memory. For this reason, it's better to implement recursive algorithm iteratively. So the question is, does iteration work always better than recursion? The answer is no. Each of these codes has its own advantages. We use recursion especially in the cases we know that a problem can be divided in similar subproblems. And when we deal with data structures like trees and graphs, the usage of recursion is more efficient. This table describes the differences between recursion and iteration. Here you can see that the first point is space efficient. You can see here that Recursion is not space efficient, as we said that it takes O(n) time complexity, but on the other hand, iteration is memory efficient. No stack memory required in case of iteration. So we are not inserting any method to stack memory while we are doing iteration. The next point is time efficient. We can again see that recursion is not time efficient because recursion repeatedly invokes the mechanism, and this leads to the overhead of method calls. And this might be expensive in terms of processor time. And also, in case of recursion, system needs more time for pop and push elements to stack memory, which makes recursion less time efficient. But as we said, in case of iteration, we are not inserting any method to stack memory. That makes iteration time efficient. Then the next point is easy to code. As you see, recursion is very easy to code. Many complicated codes can be written in recursion very easily. But when it comes to iteration, it's very difficult to write some problems in iteration. That's why if we know that we can divide a problem into similar subproblems, it's advisable to use recursion. So that's all for the comparison of recursion versus iteration. Hopefully, you understand the main differences between them. All right, in the last lecture, we have compared recursion versus iteration. And we saw that in many cases, iteration performs better than recursion in terms of time and space complexity. But there are situations where recursion is preferable instead of iteration. Now let's examine the situations where we should use recursion and when we avoid it. As we discussed in our previous lectures, the recursion is always used if we can easily break a problem into similar subproblems. So in these kinds of cases, we should always use recursion. Now the next point is that we should be aware of that whenever we use recursion, it brings with itself extra overhead. As a programmer, we might not be aware of it, but the system manages it internally. So there might be time problems as well as space problems. So if you think that system will handle it without any problem, then go for recursion. This means that recursion method that you are developing will be run on supercomputers. But there might be situations we cannot compromise either with time or space. Then in those cases, we need to avoid recursion. For example, if you are developing a mobile application, which should run on low memory devices as well, so in this case, recursion is not advisable. Similarly, if you are developing an algorithm for critical system, which must be so fast, like the airbag system in the car, where a fraction of second matter, you must avoid using recursion in these kinds of applications. So the next point here is that there might be situations when we need a quick solution. Instead of thinking efficiency of algorithm, we develop solutions using recursion. As we saw in our previous lecture, writing code using recursion is much easier. For instance, solving mathematical problems like factorial or Fibonacci, we can use recursion as an easy solution. So in the next lectures, we will see how to implement recursion methods for factorial and Fibonacci numbers. So recursion adds clarity and reduces the time needed to write and debug code. If you know your input into a function is going to be small, then recursion is certainly a good choice if you want to declutter your code. If your input is sufficiently large, however, the sacrifice of speed and memory for the sake of clarity becomes less attractive and functional. Now the next point is that recursion is very useful when we traverse a tree. It's better at tree traversal. This one is a little more advanced. An extremely simplified version of what this means is as follows. A tree is a collection of objects that are linked to one another. Imagine leaves on a tree connected by branch that are turned into connected other branch all the way to the root. Here you can see a sample tree data structure. Even though we are going to discuss this in detail in tree section, I'm just giving you a simple example here. Because recursion in a tree traversal is very efficient. One of the more efficient ways to traverse this tree when looking in a specific leaf. So we can do it by recursively following a single branch until the end of that branch, until you find the value that you are looking for. For example, in this case, if we start from here, we need to go all down till 1. So in this case, our recursion function will be very efficient. There are different types of traversal of tree, which we will discuss in tree section, but here you just need to know that recursion is very beneficial when you use pre-order traversal, where we recursively following a single branch until the end of the branch to find the value that we are looking for. Here we see that pre-order tree traversal works like this. It starts from 15, then it goes to 9, then it goes to 3, and then it goes 1. We see that this branch is finished. Then it goes to 4. Then again, it goes back to this side, which is 12. Then again, it goes here, 23, 17, and at the end, 28. We will discuss this pre-ordered reversal in 3 sections. Here, I just want to show you that in this case, recursion is very beneficial. Finally, when we use memoization inside recursion, the time complexity can be reduced. This means that if you memorize the result by saving the value of each calculation for further use in the recursive calc, you can in fact reduce the time complexity. This is also an advanced topic, and I don't want to confuse you here, so we will talk about this topic in dynamic programming section. Let's continue to see in which situations we cannot use recursion. So here we can easily say that when we face the reverse case of these cases we mentioned here, we cannot use then recursion. So if we cannot divide our problem into similar subproblems, this means that recursion cannot be used. And if time and space complexity matter for us, then recursion is not advisable. Recursion uses more memory. Because the function has to add to the stack with each recursive call and the keep values there until the call is finished, the memory allocation is greater than that of an iteration function. If we use embedded memory, for example, an application that takes more memory in phone is not efficient. And the next point is recursion can be slow. If not implemented correctly, it can be much slower than iteration. It's actually pretty difficult to write recursive function where the speed and memory will be less than that of iteration function, completing the same task. The reason that recursion is slow is that it requires the allocation of new stack frame. So that's all for this lecture. Hopefully you understand when we can use recursion and when we need to avoid it. Hi there. In the last lecture, we have looked at the cases when we need to avoid recursion and when we need to use it. Now in this lecture, we will look at how to write recursive method for any given problems in 3 steps. We learned from our previous lectures that a recursion function calls itself repeatedly until base condition is satisfied. A function calling itself is very dangerous, as it is relatively less intuitive and may run into some runtime error if we don't treat it with extreme caution. So here, I will introduce you a 3-step approach that can make you confident enough to write your own bugless recursive functions. So as an example, I will use a mathematical problem which is called factorial. In case you don't know what factorial is, let me just give you a brief explanation. Factorials were used to count permutations at least as early as the 12th century by Indian scholars. It's a product of all positive integers less than or equal to n. Factorial denoted by n and exclamation mark. This notation was introduced by French mathematician Christian Kramp in 1808. We can calculate factorial only for positive numbers, and the factorial of 0 is 1. As an example, if you want to calculate a factorial of 4, the answer will be like this. 4 multiplied 3, multiplied 2, and multiplied 1. So how did we get this 4, 3, 2, and 1? It's coming from the definition that all positive integers less than or equal to n. So in our case, n is 4. So all positive integers equals to 4 and less than 4 are 4, 3, 2, and 1. So the product of these integers is factorial of 4. Now let's say another example. If we want to calculate factorial of 10, so how do we do that? Again, we start from 10 and taking all positive integers that are less than equal to 10. So we know that all positive integers that are less than equal to 10 starts from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So if we multiply all of these numbers, we are getting factorial of 10. So based on these points over here and the examples that we provided here, we can express the factorial of n like this. This is the base equation for factorial. Now let's see how can we find out this factorial of any given value using a recursive method in 3 steps. So the step 1 is recursive case, the flow. When we create a recursive function, the first thing that we have to do, we need to identify the recursive case. In our case, which is how a factorial function is defined using factorial functions. So we have identified that the general expression for factorial is like this. So how can we write this recursive function to have a factorial on both left and right sides of this equation. So if you look at this carefully, we can see that this part is over here can be expressed n minus 1 factorial. If it is not clear, let's calculate the factorial of n minus 1 separately. So the factorial of n minus 1 is calculated like this. N minus 1 multiplied with n minus 1 minus 1, then multiplied with n minus 1 minus 2, then it continues until we reach 1. If we do some calculation here, we are getting the value over here. And you see that this expression over here is equals to this expression. So this means that we can change our function something like this. N factorial is equal to n multiplied with n minus 1 factorial. In this case, we have successfully found a recursive case, which means that on both left and right side of equation, we have factorials. Now we have identified the recursive case. Let's switch to Visual Studio Code to develop this case in Python. So here I will create a function, factorial, which takes n as a parameter. Then it will return the expression that we have over there, which is n multiply with n minus factorial, n minus 1 factorial. So this is our function for this expression over here. As you can see, we have just developed the recursive case in the Python. So our first step of identifying recursive case is done. In this code, you can see that our factorial calculation is almost done. You might be thinking that this function over here is enough for calculating factorial. But there is a bug in this code. Let's try to find it. Let's run this function for factorial 3. So here I will put factorial 3. So to see what's going on, I will just add here print function, which will print n, because otherwise we will not see what's going on. So if I now run this function, we see that Python raises error saying that maximum recursion depth exceeded while calling a Python object. This means that we have a limitation to keep number of methods in stack memory. Basically, it's possible to increase the stack memory. We can, for example, here, we can import sys, and there we can increase stack memory, import sys. Then if I do like this, sys set recursion limit. In this case, you see that it's 992, but if I do it, for example, like 10,000, and rerun our application, we see that it comes here 9,992. So we can increase the stack memory, but here our goal is not to increase stack memory. Our goal is to prevent this situation. If you go back here, you see that our function get called 10,000 times and never stopped. Because the recursion limit in Python is reached, that's why it stopped. So this means that there's a bug inside our function. So here we see that the function keeps calling itself without stopping. This will lead to a system crash if we implement it in an application. So the question is, how do we need to prevent this case? So to prevent this case and write bugless code, we need step 2. So let's see what's step 2. Step 2, base case, the stopping criterion. As you remember from previous lectures, we need a base case to prevent infinite loop. So here, we need a base case for our recursion function as well, where it stops calling itself. So how can we do that? As we said in the definition of factorial, that factorial of 0 is 1, and it's obvious that the factorial of 1 is 1. So as a base case, we can use these conditions over here. So let's return to our code. Here, I'll just delete this one. Let me just delete this one as well. As a base condition, I will write an if condition over here. If n in 0 or 1, then we will return 1. Otherwise, the function will call itself recursively. So here we will put like this. So now we have added base case in our function. So if we rerun our function for factorial 3, we will see that this error that appears here will be disappeared. So I'll print the value from here as well, print function to here to see what is the factorial of 3. So if I rerun this code, you see that it calculates the factorial of 3 as 6. Let me just clear here and put, for example, factorial 4 here and rerun our code. You see that it calculates, no, I haven't saved this, that's why it gives me 6. After every change, you need to save the file because as you see that I have a sign here that I haven't seen. If I click save and rerun this function, you will see that the factorial of 4 is 24. Now here one more time, you might think that we are done with our code in 2 steps because our code works the way as we want. So why do we need third step? So here, I want you to pause the video, think if you can find what's missing in this code. Okay, let's see what's missing over here. The most important thing to consider when writing a recursive function is making sure that function stops for every possible argument n. So here, we need to identify in which case it doesn't stop. So for this case, we have step 3. Step 3 is unintentional case, the constraint. We have base condition for our function, which is for when n equals 0 and when n equals 1. And our recursive case calls the function itself with an argument n minus 1. This means that the function will reach a base case only if factorial n starts with a non-negative integer. So from definition of factorial, we know that it is calculated only for positive numbers. So if we run our function for minus 1 and 1.1, what will happen? Let's rerun it and see what's happening. Okay, if I put here minus 1 and save it and rerun it, you see that again we are getting the error that we got before, which is maximum recursion depth exceeded in comparison. This means that our function again inside infinite loop. So we need to prevent this case as well. While there are different methods to achieve this, we will use a simple assertion method in Python that throws an error if n is not a non-negative integer. So if you don't know how the assertion method works in Python, in the resource section of this course, I have attached a PDF file which shows the logic. Basically, what we are going to do here, before if condition, I will write assert case, which checks n is greater and equals to 0, and the second case is n has to be integer. So an integer equals integer. Otherwise, it will raise an error. So the error will be like this: the number must be positive integer only. Basically, this line of code makes sure that n is a positive number and it's integer. If not, it will throw an exception that the number must be a positive integer only. In other words, we are forcing the argument n to be a non-negative integer. So now our function is ready. So if we run the same case for this function with minus 1, you will see that it gives another error saying that number must be positive integer only. This means that our function is not anymore inside infinite loop. So again, if you run this function for 1.5, you'll see that the same error comes over here. For example, if we run our function for 10, we need to calculate 10 factorial. You see that it's calculated as the way that we calculated. So with this, we have implemented last step successfully for our recursion function of factorial's number. To make things more clear and more understandable, let's run this function for any integer number and see what's happening behind the scene. So I will just copy this function from over here and put it over here. For simplicity, let's run it for when n equals 4. If we run this function when n equals 4, the control comes to the first condition where it says n is greater and equals 0 and n has to be integer number. So we see that 4 is greater than 0 and it's an integer number. So everything okay with this case. So it will continue to the next case. In the next case, we are checking that if 4 is 0 or 1. We see that 4 is neither 1 nor 0. So the controller comes to the else statement. What's the else statement? It says n multiplied with factorial n minus 1. So what's right now n? It is 4. So n is multiplied with the return value of factorial n minus 1, which is in our case 4 multiplied with factorial 3. So we don't know the return value of factorial 3, which means that our controller will call this function recursively. So the controller once again goes to the first line. Here again we check that whether 3 is greater than 0 and if it is an integer number. And we see that all cases are okay here. So we continue to the next if condition. Here we see that n is not 0 or 1, which is 3. So the controller will continue to the else condition. Now one more time in else condition, we have a return value which is n multiplied with factorial n minus 1. So in our case, n is 3. So it will be 3 multiplied with factorial 2. So here one more time we see that we don't have any return value for 2, which means that our function will be called recursively once again. So the controller will go to first line again. Here we don't have any problem for 2 again because 2 is an integer number which is greater than 0, and it will continue to the next condition. And in the next condition, 2 is not 0 or 1, which means that this controller will go to the else condition as well. In else condition, we have n multiplied factorial n minus 1 one more time, which means that in this case it will be 2 multiplied with factorial 1. So this means that one more time we will do a recursive call to our function. So when we call our function with parameter of 1, so the controller one more time goes here, it checks that 1 is greater than 0 and it is integer number. Then it goes to the next condition. Here we see that n is equal to 1, which means that this function over here will return 1. So the return value of this function is 1. So if you have the return value of this function, we can easily calculate the return value of this function over here, which is the factorial function taking the parameter of 2. So the return value of factorial 2 is 2 multiplied with the factorial 1. So we know that factorial 1 is 1. So 2 multiplied with factorial 1 will be 2. So now we have an output for this function. So the factorial 2 is 2, which means that we can calculate the factorial 3 because the return value for factorial 3 is 3 multiplied with factorial 2. So in this case, the return value for factorial 3 will be 6 because 3 multiplied 2 is going to be 6. Then from here, we know that return value for factorial 4 is 4 multiplied with the return value of factorial 3. So we have calculated the return value of factorial 3, which is 6, and 6 multiplied with 4 will be 24. So the factorial for 4, so this is how we recursively find the factorial of any given number. Here I try to show you that when you call a factorial function recursively, what's happening behind the scene. And behind the scene, you saw that every time the function calls another function which is 1 or less until it reaches the base condition that we have a return value. If we don't provide the base condition over here, our function will be inside infinite loop. Now in this lecture, we have introduced you how to write a recursive method in 3 steps, and hopefully you understand it. And I gave an example of factorial using these 3 steps to write a recursive code. Hopefully everything is clear now. Hi there. Now in the last lecture, we have looked at how to write a recursive method for any given problem in 3 steps. As an example, we have used factorial numbers. Now here, we will look at different mathematical problem, which is Fibonacci number. And by using our 3 steps, we will create a recursive method to calculate Fibonacci numbers. So before starting to write our function, let's clarify what's a Fibonacci sequence. Fibonacci sequence is a sequence of numbers in which each number is the sum of 2 preceding ones, and the sequence starts from 0 and 1. The typical Fibonacci numbers sequence will look like this. As you see, the sequence starts from 0 and 1. This means that the first 2 elements of Fibonacci numbers are always reserved for 0 and 1. So the next number is the sum of preceding 2. Here, in this case, 1. 1 is the sum of 0 and 1. And the next number is 2. This one also is the sum of these 2. 1 plus 1 equals 3. And if we continue to the next number, we see that we have 3 here, which is the result of 1 plus 2. Then it goes like this. Here we have 5. 5 is the sum of 2 and 3. As you see, each number is the sum of preceding 2 numbers. And this is the logic behind Fibonacci number. So hopefully you understand the logic of Fibonacci numbers. Now let's see how can we calculate Fibonacci number for any given number using recursion. As the first step, we need to define our recursive case. So if you look at the sequence over here and take n number from this sequence, we can easily define the recursive case. For example, if we take 5, we see that 5 is the result of two preceding numbers, which are 2 and 3. So based on this logic, we can create a recursive case. So our recursive case for these Fibonacci numbers will be like this, which is Fn is equal to Fn minus 1 plus Fn minus 2, which means that in this case, 5 is n. So here we go to Fn minus 1 will be 3, and Fn minus 2 will be 2. Take into account that we are not just summing the numbers, we are taking the result of these functions. So based on this condition, we can write our initial version of Fibonacci function. So once again, I will switch to Visual Studio Code and write a function there. So here I will define a function which is Fibonacci. The function will take n as a parameter. Then here it will return Fibonacci n minus 1 plus Fibonacci n minus 2. So this is the initial version of our function. So if you run this function for any given number, let's run it, for example, for 5, Fibonacci 5. We see that again we receive maximum recursion depth exited, which means that our function again keeps calling itself without stopping, which is infinite loop. So this will lead to system crash if we implement this in any application. To prevent this case, we know that we have a second step in which we define a basis condition for our method. So how can you define the base condition for each method? To find out what will be the base condition, let's go to the back our definition. Here in the definition we see that our sequence starts from 0 and 1. So which means that if we select as a parameter 1, the Fibonacci of 1 is 1. If we select parameter as a 0, the Fibonacci of 0 will be 0. This means that we can use 0 and 1 as a base case. But here when we reach these cases, we will return them itself. So if I go again back to our Visual Studio Code, here I can write my base condition. If n in 0, 0 or 1, then this function will return n. Otherwise, this function will call itself recursively. Here, take into account that the function calls itself twice with different parameters. So if I run this function for one more time for 5, let me just print this out. We see that the Fibonacci of 5 is 5. Now when we run this function for 6, we see that the output is 8. So this is the 8 is the 6th number in the Fibonacci list. Let's go back to our list to see that if this is correct. Here we see that it starts from 0, 0, 1, 2, 3, 4, 5, 6. The 6th element is 8. So if we run our method with 7, we will receive 13. Let's check it. I'll change the parameter from 6 to 7 and save it and rerun it. You see that we receive 13. Now everything seems alright, and we created base condition for our function. So our function works very well. So here we need to go to the third step. But before going to third step, I want you to pause the video and think about what will be in the third step. What's the bug inside this code? Alright, let's see in which situation our function might run an infinite loop. From the definition of Fibonacci sequence, we know that it starts from 1 and 0. And this is applicable only for positive integers. So here again, we need to take into account that the number is not negative and it has to be integer. So as an unintentional case, we need to check these cases, because we didn't take into account that the parameter might be minus, the parameter might be negative number or not integer number. So let's switch to our code and check these cases. If I run this function with minus 1 and run this function, you see that again I'm receiving this error which says that our function is infinite loop. So it reached maximum recursion depth. Then Python automatically stopped our loop. So let's run up our application for non-integer number. So here I will put 1.5 and run it. Here again I see that I received the same error, which means that there are some cases that in which our function will run in infinite loop. So to prevent this case, once again, we need to check the case that the number should not be negative number and it must be integer. So we did this in previous lecture. Here is going to be the same. We will use assert method from Python. And greater and equal to 0, and n has to be integer. Otherwise, we will raise error saying that Fibonacci number cannot be negative number or non-integer. So if I save it and rerun this function for this case, let me clear here. We see that we receive different error, which says that Fibonacci number cannot be negative number or non-integer. So if I run this for -1, you will see that we receive same error. So here again we receive same error. But if I run it, for example, for 7, we will receive 13. So with this, our function is working properly. So here we show that how can we create Fibonacci function using recursion, and we took into account our base condition, and also we prevent the cases that might cause our function to run infinitely. Once again, I will copy this code to show you what's going on behind the scene when you run this function. Okay, now let's look at what's happening behind the scene when we call this Fibonacci function for parameter of 4. So if we call this function for parameter of 4, the function first goes here, it checks first condition, we see that 4 is greater than 0 and it's integer number. Then it continues to the next condition. Here we see that 4 is not 0 and 4 is not 1, which means that the function will go to the else condition. In else condition, we are doing recursive call twice to our function. The first one will be n minus 1, which is in our case will be Fibonacci with the parameter of 3, and the second one will be n minus 2, which will be 4 minus 2 is 2. And this function will call these two Fibonacci functions recursively. So once again, we see that we don't have return value for Fibonacci 3. So our controller will go to the first line. Here, it will start to check again. The first condition is again fine for us because 3 is greater than 0 and it's an integer number. And here we see that it's not going to this condition, and it will go to the else again. Here, our function will call recursively again twice. So when calling a Fibonacci function with parameter 3, it will call two different functions recursively. The first one will be with the parameter of 2, and the second one will be with the parameter of 1. Now, in this case, we have another function over here, which is calling recursively as well. When we call the function for parameter of 2, again, our controller will go here. We see that it's greater than 0 and it's an integer number and it is not going to this case, which means that it will call recursively as well. In this case, the first function will be 2 minus 1 is 1, and the second function will be 2 minus 2 is 0. So here, one more time, our function will be called recursively. Now, before continuing here, let's continue here to see that what's happening over here. It's going to be same as we called here. You see that when you call Fibonacci function for parameter of 2, it calls two different functions over here, which is one with parameter 1 and the other one with parameter 0. From here, if our function calls with the parameter of 0, the controller will go to the first line, and we see that n is equal to 0. So 0 is an integer number, and it continues to the second condition. In the second condition, we see that n in 0 or 1. So 0 equals to 0. So this case will work, which means that the function will return 0. Then the next function, which is Fibonacci function with parameter 1, when we call this, it's again passes through the first condition, it goes to the second condition. In the second condition, when n is equal to 1, it returns 1 as well. So here we have 1. So if we have these two values for these functions, we can get a value for Fibonacci 2. So in this case, 1 plus 0 will be 1. So we know that for Fibonacci 0, the return value is 0, and for Fibonacci 1, this return value is 1. So in this case, this function will return 1, and this function over here will return 0, and this function over here will return 1. And again, we calculated Fibonacci 2 over here. We know that it's 1, so we will put 1 here. I don't want to go through all steps here, because once we did this, it will be the same here. So it's 1. So we have a value from here for Fibonacci 3 and for Fibonacci 2. For Fibonacci 3, it will be 1 plus 1, which is 2. So when we sum up these two values, we will get Fibonacci number for 4, so which will be 3. So if we go to our list and we count it from 0, 1, 2, 3, 4 is 3. So this shows that our function works properly, and I showed you how the function works behind the scene. Hopefully everything is clear now. With this second example, I hope that creating recursive function with 3 steps is now much more clear. So see you in the next video.